Hi, I see you're admiring the beauty of the plasma ball. But have you ever wondered what plasma actually is? Let's start by taking a look at the simplest of atoms, the hydrogen atom, which is made up of one proton and one electron. Now, we take a bunch of these atoms and place them into a container. These atoms are bouncing around, taking up all the available space in the container. This is how gas behaves in an enclosed space. When we increase the temperature of the container, the atoms will become more energetic. Eventually, some of them will lose their electrons, resulting in the formation of plasma. Essentially, plasma is formed by adding a large amount of energy to a gas, leading to some atoms in the gas becoming positively charged ions due to the loss of electrons. But there is another type of plasma, the Quark-Gluon Plasma. It's extraordinary form of matter. To understand it, let's start from the beginning. Protons are composed of two up quarks and one down quark. All of them have color charge. You can think of color charge like the electric charge, but instead of two kinds of electric charge, there are three kinds of color charge. This has nothing to do with actual colors in the same way that the electric charge has nothing to do with being positive or negative. Color charge is just a name for a certain property of quarks. So, the protons are made of quarks and also of gluons. Gluons constantly exchange the color charge between quarks. It's similar case with the neutron, but with two down quarks and one up quark. For now, let's stick with proton. In order to extract the quark, it is necessary to introduce energy into the system. As Einstein's famous equation teaches us, mass and energy are interchangeable. The energy required to separate a quark from a proton is so huge that it is enough to produce a pair of new quarks. So we will end up with proton and pion, which is composed of a down quark and an anti-down quark. Therefore, the observation of free quarks becomes impossible. Imagine we take two protons, accelerate them using an electromagnetic field, and observe the collision. As a result, a variety of particles, mostly pions, are produced. Now, let's explore what happens when we turn our attention to the collision of two lead nuclei, each made up of 208 nucleons. One could imagine that a collision of two nuclei would be a simple combination of collisions of protons and neutrons. But this is not the case. When the collision energy is high enough, we could say that protons and neutrons melt in this object. The result is a large soup of quarks and gluons, which we call a quark-gluon plasma. This soup has different properties than a simple pair of colliding protons or neutrons. Its basic elements are no longer particles made of quarks, but quarks and gluons themselves. We call this deconfinement. Just like regular plasma, the quark-gluon plasma exhibits unique properties that arise from the freedom of its basic building blocks. In this deconfined state, quarks are characterized by their actual, considerably smaller masses, rather than the masses they possess within particles like protons. This makes the production of so-called strange quarks easier. As a result, we expect an increased production of particles containing strange quarks, like kaons. We call it strangeness enhancement, and it is considered a classical signature of quark-gluon plasma formation. But why should we care about quark-gluon plasma at all? Well, it's a state of matter called the early universe, so a few short moments just after the Big Bang. Investigating this extraordinary state of matter can shed some light on the most fundamental questions about the origin of our universe.